I cannot do. No, it's fine. Okay. You didn't expect it, right?
No, I mean, the last 2 years, so yeah, I don't need to introduce Valerio, I mean, especially, but maybe a couple of younger people. So Valerio finished his PhD at, but you have to check, École Polytechnique, Lausanne, on the magnetic nanostructures.
Correct.
This is maybe kind of surprise, but then he moved at around, when you finished 2000.
2000, yes.
Then you moved to do postdoc in Geneva with Nicolas Gisin. That's the time where we
started meeting, yeah.
And he was there also as a different positions, also kind of system position until 2007. And then he moved to Singapore, to NUS Singapore from 2011. You're a full professor at the National University of Singapore. He is known for his work on non-locality, first and foremost, but also on the past research. I found it on the web that you define this as a past research line, which is a quantum key research. And then still on quantum non-locality, quantum thermodynamics, foundations of quantum physics in general. And he also wrote a couple of books, some of them science popular, and the last one was, I think, was Tell Non-Locality, and I really can suggest you, I mean, if you want to enter the field, to get it and read it. And today he will talk about a topic
something
that he hopes to provoke other people to look at it. It's about complexity of quantum states.
Yep, something like that, yes.
Okay.
Thank you. In fact, this is not going to be a talk. I'm very happy that there are so many people here ready to give me feedback. That's the goal of this operation, right? So these are thoughts that I wanted to share with people because are really not well-developed thoughts in a sense, right? It stems from a feeling that there is a question that I would have liked to address many years ago. Somehow I met mathematical and conceptual obstacles trying to, mathematically is obvious for those who know me, I'm not as good as many people here in this room in mathematics, so at some point, although as a disclaimer I have to say that when I presented this in a group where there was David Gross, he told me, wow, these are difficult things. And if David Gross tells you that, you know that you are in trouble, right? So maybe I just didn't take the right path to publish the right things, right? I just went straight into the wall. So I really, I mean, it would be a mess, a kind of thought going around, and it's not impossible, as some of you will tell me, that I have not, I'm not aware of very important things, right? So I mean, that's really why I'm giving this talk, right? So I'm really hope that some of you, either here or later, will send me an email or even now and say, you should read the papers of, or the book of, and so on. It's okay, and I will do it, right? So that's really, please, this is not a master class, it's more like sharing some thoughts. So where do we start from? Okay, let me start from the maybe applied motivation. It's never my motivation, but there can be an applied motivation. I mean, and let's apply to outreach. As you probably know, we don't know yet where is the power of quantum computing coming from. Right? So we know that there are some algorithms that provably, you go through the calculation, Shor's algorithm, maybe Chaslav teaches it in his module, I will have to teach it in my module when I go back to Singapore for the first time. You go through Shor's algorithm, you do a calculation, say, wow, this is scales in that particular way, much better than anything we know classically, right? It's okay, it works. Grover's algorithm goes like that. Many others that actually are a combination of these two, but why, right? Now, if I give you a new algorithm, we don't have any way to say, oh, yeah, this is likely to work, this is likely not to work, or there is a principle behind that, right? Contrary, for instance, to quantum cryptography, where at least we have two, if not three, physical ways of motivating it. There is the no-cloning theorem, there is a measurement modifies the system, and there is no locality, right? If you do the entangled system, you say, well, the information did not pre-exist, or even nothing to read, right? And otherwise, so there we have something like, okay, something, and we know, for instance, famous theories in quantum cryptography, right? If the channel is entangled and breaking, there cannot be any security. Well, because, well, for this reason, right? So now, thinking as a non-expert of the field, so, okay, maybe my current understanding, again, here may be wrong, is that there is only one community of people trying to address seriously this issue of where in a systematic way, where the power of quantum computing comes from. And these are the people that stem from, let's say, Robert Rausendorf and others, that stem from all this magic state quantum computing thing is a particular way of implementing quantum computing, for those who don't know. And in that framework, a few years ago, there was a work by Emerson and others that they claimed that contextuality was the resource behind quantum computing. Then other people started saying that it's negativity of something, of Wigner functions, generalized Wigner function for discrete systems, and so on. They're still working on that. Last year, Rausendorf published a paper saying that they don't need any negativity, creating a scandal contradicting essentially all the other theorems, but not really, because there was an assumption, and so on. It's in a community and now apparently it's all about constructing a very messy polytope. So Miguel, please, that's your business. And they are there trying to find the facet of this polytope and so on. So it's very specific. So, well, before even all this started, in my thoughts, my idea was very simple, and sorry if it's too naive maybe for you, is that to me, a quantum algorithm or a quantum computer or something will be useful if the following happens. If at some point, a necessary condition, not sufficient, Radim can confirm, necessary condition, the algorithm at some point must create a complex state, and it must create it in a short time, right? Why? Because if you don't create a complex state at some point, you can simulate it classically. If you take a long time to create that complex state, well, it's not useful, right? Because it's all about time, right? So without putting any number on these things, right? To me, that's the intuition, that we should try to find not only shorten the circuits, like in complexity theory, many people nowadays are trying to shorten circuit complexity to realize what? Shor's algorithm or Grover's algorithm, right? Try to compact these gates. But the question is, what is the complexity of the object that comes out of these? Of course, I'm thinking a circuit model, right? If you were to think in a measurement-based model, probably you have to phrase these things slightly differently, okay? So now the question is, what is a complex quantum state? And that's something that, honestly, well, I haven't found any reasonable definition for that. And how do you certify even that the state is complex? Because with matrix product states or networks or whatever, you can certify probably that something is simple, right? I can create that state with matrix product state, matrix of dimension 2 by 2 or 3 by 3 and so on, right? And then it doesn't scale in a particular way, or maybe it's the constant depth of the matrix, then fantastic, right? I can do many body physics. But what would be a complex state? Okay, so let me introduce to you the notion of tree size that Aronson introduced in the year, I think, 2009, in order to try to make some funny mathematics out of a challenge. The challenge was one of these many challenges. I forgot who put it. Maybe already Jill Kalal. I don't know if it was already there. Some people already at the time claiming that quantum computing will not be possible because we don't have any evidence that complex states can be realized in quantum physics, whatever that means. And this was all, again, in the air, right? A complex state cannot be created. And Aronson said, okay, let's play the game. Let's try to define what a complex state is. To the best of my knowledge, he's the first one who tried. Again, the best of my knowledge may not be the best at all, but that's... So what did he do? Well, he did it for pure states. So he called it tree size. Tree, like tree size. And the thing works like this. Is the minimal, well, it's a bit hard to define in words. Is the minimal number of cats needed to represent the state. Example, let me give you a very simple example. The tree size of the W state. Okay, the three-sided W state. W state is like this: 0, 0, 1, plus 0, 1, 0. Why I start with this would be clear that the other ones are kind of obvious, right? The G and Z. So, well, you look at that and you say, well, 9, right? No, in the computational basis, right? Thank you for, in the computational basis and respecting the tensor product structure, which is something that I'll come back to later. Indeed, that's one of the points. Czaslaw, he always anticipates my things. He's thinking so fast, right? Anyway, so one way you can simplify the number of cats, and you find this completely obvious, right? Remember, this is the thing that David Gross said it's very difficult to do. So when you generalize, right? The one for quantum information. So what I could do is this, of course. There I cannot do much. I get 8. And now, you need to prove, it's one of the things we proved in our papers, is that that's really the minimal. You cannot do better than that, even if you don't choose, even if you were to allow a basis to be different. For instance, I could, this doesn't need to be 0 and 1, for instance. It could be 0 and some superposition here. Right? So there's no way of writing the W state with less than this. Why does it call it 3 size? Because the idea is to count the leaves of a grounded tree. So how do you create that thing now? OK, so this thing, I can create it like this. I can start with, what do I need to do here? I forgot how to do it. OK, I start with 0 here. And then I have 0, 1. This 0, 1, I tensor them. And then I would tensor 1 and 0. Sorry, I should do it. You see, I'm too fast in these things. 1, 0. I also tensor them. This is this. And then I get my 1 that gets tensored. So here I will tensor now these 2 branches. Then I tensor these guys. And I put a plus. So the idea of the trees is that essentially you start always with a tensor, then you put some plus, then a tensor, then a plus, then a tensor, then a plus, and so on. You construct it like this, right? And that's the tree. Of course, a computer scientist looks at tree from the upside down, right? We would rather put this. So these are the leaves. Okay?
Can you also use coefficients?
Yes, you can. Now I could use coefficients, so I could put I could decide that here I put a 2 in front of these. Of course, I would get a 2 here, and I would put a 2 on this branch, and so on. Now, the problem is if I put a 2 here, it's no longer guaranteed that this is the minimal decomposition. That's where it starts becoming complicated. In fact, I don't remember it by heart, and maybe I should have done a more formal thing here. If you go to the most complex state that we computed of size 4 of 4 qubits, that has 16 leaves. If you write it in a very particular way, but if you change the coefficient, it has fewer. Right? So it's really, of course, the basis in the sense, because you can allow for any basis. Right? So I can allow local operations here. Again, here I could have, this 0 could be something else than that. Okay? Anyway, so that's the, why did Aronson define it like that? Well, first of all, because indeed, it tells you how long it takes to write it, right? It might be a definition of state, right? If I want to write a paper with the most complex state of 10 qubits, maybe it takes me 5 pages, right? And then if I really want to write it down explicitly, so that's why.
Computer programming, in MATLAB or whatever, right? I mean, you want to represent this state as a vector, you do this.
But it did, but that's we will fix the base, but now I want to minimize on that. So the thing is not trivial at all in this thing is that I told you that without the 2, this is really the minimal I can do for that state. Right? And then now I cannot improvise, but later I can show you examples where indeed these things, the 1 of 4 qubits is funny because in order to do the minimal decomposition, you need to do something like this. The minimal decomposition looks like that. There is a phi plus, so by phi plus I mean this, already 4. Huh? There is a phi plus of 1, 2 that gets tensored with a phi plus of 3, 4 with some coefficients. And then here there is a phi plus of 1, 3 that get tensor with a phi plus of 2, 4. And then you, you tensor those, and you sum. So somehow, if I were to write the leaves here, this would be 1, 2, 3, 4, and this would be 1, 3, 2, 4. I would have to cross the branches somehow. If I don't do that, then the complexity of the same state would be 18. So that's also why we were not able to generalize it beyond 5 qubits, because that I don't see any structure. So suddenly, sometimes you hope that for 2 is clear, right? For 2 is the Schmidt decomposition. Any 2 qubit state with Schmidt decomposition, 4, right? For 3, G at Z, obviously 6, right? 0, 0, 0, 1, 1, 1. And this is a bit higher. And for 4, well, that is something like that, whatever that is. Okay, but Aronson, of course, this is what we did at some point, because again, my mathematics are whatever they are. I can do only few qubits. Aronson relied on a theorem by a friend of his in the same conference of computer science that proved that some states can be provably of superpolynomial, some family of states can be provably of superpolynomial tree size. Let me give you just an example that I remember, because there are a few others. Is what is called the determinant state, or else the permanent state, or else the Hafnian state, or whatever you want to put there. And it's something like this. So you take your it's a state for n square qubits. And the idea is that you take your qubit thing, right? So the representation 0, 0, 0, 1, 1, 1, 1, 0, and so on. And you arrange it as a square matrix, however you want. There are square of them, right? So you just arrange, let's say, there's 25 here. I take the first 5. The other ones, I start writing them there, and so on. So I write these 25 coefficients as a matrix, and then I compute the determinant, sum. So psi sum over x, the strings of n qubits, 0, 1 to the power n qubits, this, yeah? Determinant of the matrix that represents is x times the computational basis x normalized. Of course, the normalization doesn't affect this thing. And then the determinant or permanent of this matrix, or any of these Hafnians, that depends which signs you switch, all these states have been proved to have a super polynomial tree size in the function of n. So if now n grows, the tree size of this thing is at least is more than polynomial in n. And of course, that's what they like, right? The computer scientists like that the things scale. Now, at this point, I can throw a few conjectures around for those who like this tree size. Again, if you want to arrange, I remember David Gross said it's difficult. For instance, I told you that for few qubits, we had the minimal tree size. So the maximal tree size, the state with largest tree size scales like these. So there is a kind of obvious conjecture, right? And how would you scale? But we've not been able to prove it, and we don't have the example, right? So I would really like that someone, maybe in a constructive way, without having to write down all the thing, would be able to prove that this is 2 to the n, right? We have a bound that is 2 to the n plus something. So there is a bound just by doing, let's say, essentially Schmidt decomposition in a compact way, that you get 2 to the n plus something like, it's something like 2 to the n, and then 1 minus 1 plus something 1 half. Yeah, there is something here that is plus 2 to the n minus 1 or something like that. So there is something that that is not too good, it's not too bad either.
Do you have a constructive proof, or like an upper bound or a lower bound?
Upper bound, I have a constructive proof.
Yeah, upper bound you can prove, right?
Yes.
Yeah.
Yeah, lower bound, no, I don't have a lower bound. That would be essentially for the maximum, right? Of course, for the minimum, it's always you can always have n, right? You just take a product state. Yeah, for the upper bound is really counting. Again, improvising here, I don't remember, but if I look at it, it's obvious how you count, right? You start essentially, well, you start from the previous one, right? So, and then, okay, so yeah, it goes like that. It goes like that. So, of course, if I have a state of n plus 1 qubit, I can always decompose it as 0 times a state of n qubits plus 1 times another state of n qubits. Okay, and if I know the tree size of this guy, the maximum tree size of this guy, and the maximum tree size of this guy is n, right? So, so this is, let's say, n, Ts of n. Then I know that Ts of n plus 1 is at most 2 times Ts of n plus 1. Right? Because I add 1 qubit here, I add this tree size here, I add 1, so I need to add 1 leaf, and I have 2 copies of that. And if you operate this, but somehow with the example, so this would not converge to the n, converge to something else. Somehow, it turns out for the examples that we found that any of this thing of this type can be rearranged in such a way that this guy disappears, but for these examples. Okay, so it's like we can somehow here we can rearrange this thing in such a way that 2 leaves in this obvious construction disappear, and that of course would give 2 to the n. Whatever, stupid conjecture, seems to be easy to prove, but, and of course I would even love to see but you see, definitely the conjecture requires that you are able to do some local change of basis that simplifies the structure of the state. And
so this is not known for the tensor rank too, no? Because if you can prove that the tensor rank is upper bounded by n, then n squared is not this upper bound, right?
The tensor rank.
Well, it reminds me, even this construction reminds me of this idea that he has to multiply 2 matrices, right? I mean, he can map it to a three-party entanglement problem.
Okay, well, that's the kind of feedback that I'm welcoming. So send me the papers and I will read them. I mean, clearly it must be super polynomial, these things, right? And of course, you can prove for some classes, like for instance, if you have matrix product states with fixed dimension matrix, then the tree size is not super polynomial, it's polynomial in that number, and so on. So, okay, somehow, you know. And finally, what Aronson also proved under a conjecture of mathematics, not p equal to np, but some other things like that, is that the state that appears in the Shor's algorithm would have super polynomial tree size, provided something is true in some number theory setting, okay? Yes?
Valerio, I didn't catch what you said to introduce this idea, but was it Scott? Was it Aronson?
Huh?
I didn't catch what you said to introduce the tree size
Yes.
idea. Was it Scott Aronson?
Yes.
Oh, okay. I missed the word.
And I don't know, okay, since I don't know Scott well, I didn't never ask him how he introduced it, because it's kind of a coincidence. In the same conference, these rats produced the theorem that on multilinear functions or whatever it is that matches these. So I wouldn't be surprised if the two of them were discussing, and then one of them wrote a mathematical paper, the other one wrote the more cat paper, and so on. But yes, it was introduced by him, as far as we know, and no referee ever told us the opposite. Yes?
So, I don't know if I'm missing something. I didn't quite really convinced that this is a good measure of.
Neither am I. Okay. Yes.
But why are there some evidence or some data to support? Because okay, it makes sense. It's very beautiful. But why would this quantify complexity?
I think
people in the field, they claim that they write. That they just.
Okay. There are 4 papers in tree size. Okay. The original one of Aronson and our 3. One of the reasons why I'm speaking of this is to try to interest people to work on that. So
Can you repeat this statement that you said that he showed that Shor's algorithm under
So,
certain conditions?
under some condition, the state that appear at some point in Shor's algorithm after you've done earlier, it would require indeed super polynomial tree size in the scaling of the problem.
So in the sense that if it's not scaling, it won't work.
Well, that would be the idea, right? The idea would be that you need that would be the idea. At least is a sanity check, right? If what comes Shor's algorithm, we know it works. I mean, it has an advantage, right? Or at least so if in Shor's algorithm the tree-size complexity would be trivial, then you would say, well, you know, then sorry, this really doesn't work, right? Well, he proved that it probably is not trivial, right?
But so here is just a kind of intuition. So one could probably, in order to combine some of them, you need some kind of good relation between the amplitudes.
Yeah.
So if you just throw it random, then
Yes.
up to the normalization, it seems very hard that you will get any structure.
Absolutely.
But then this sounds a little bit as this paper's like too much.
Too much entanglement.
It doesn't work as well.
Yeah.
So it's neither too high. I mean, I don't know.
And that's, remember that my thing has two parts, right? This is how to quantify, not. This is the only proposal I know, probably not the correct one, on how to quantify the complexity of a state. Next, you have to tell me how long is the circuit that leads to that thing. The dream would be to prove that the states that are useful are those that have, the states that you mentioned, that are those of that paper that are too entangled to be useful. Indeed, it's because maybe it takes too long time to prepare, right?
You need a lot of entanglement to prepare a big tree size, right?
You need a lot of, well, you know, that
Bounded by the Schmidt rank of the last
correct,
part.
correct. So that paper is, I mean, of course, we all remember the title, but that paper is a technical paper. It uses the geometric entanglement as a measure. Nobody's ever proved the geometric entanglement as any operation whatsoever, right? As far as I know, again. Certainly not for quantum computing. So it's a nice result. They put a title that sells very well, so we all remember it. We old people, maybe the young people have not heard about that. But it's a technical result. So nobody really proved that. One can say, okay, sure, maybe there is, as you say, maybe we need a lot of entanglement according to another measure, right? And that measure would be, it's certainly true that there are entangled states that are very entangled and are completely useless.
Wasn't there this paper by Martin van den Nest? Did you read it?
Yes?
Like expanding on the Deutsch-Joshua idea, which was kind of similar, no?
I think, yeah. We cite it now that you mention it. We cited it. This paper, these works are for 6 years ago, so we cited it, we studied it, and we forgot, and I forgot about it. Right? My students by now are doing other things. Who was involved in that? Tin, you're not involved in this one, right? Nguyen, Sayu, and Xinja, right? These were the people. Tin was hanging around at the time in the group, but was not working on these things. Okay, yeah, so yeah, I mean, all these questions that you mentioned are indeed fully open, right? So this is, again, I told, maybe nobody here has raised their hand to say that there is another measure of complexity. Of course, you could think of taking a tensor network and say a measure of complexity is if the tensor network scales, well, in a particular way, right? And then I would call it complex like that. Okay, that's another possibility. This is the only one that I know that has by the way, is in principle computable, right? You go through all possible decomposition of your state, and of course, it's not efficient at all, right? But it's not incomputable in one of these measure of complexity that would be undecidable, right, or whatever. That's decidable. Yeah, probably Heisenberg is one of those. So it's computable in principle. It's a mess to compute, and it's only for pure states. Of course, now try to extend to mixed state. You can only put a little bit of noise and see the mixture and whatever, right? So a lot of open problems for those who are interested. Maybe you say, no, I don't care at all about these things. So then, fine.
So just one comment.
Yes?
I mean, it seems like in all of this discussion, as soon as you fix a complexity measure and you say typical states have typically a high complexity measure,
Yes.
you will always have the property that most states have a high complexity but are still useless for quantum computation.
Correct.
So you need some kind of atypicality property. That's probably what you said.
Yes.
That they have a short circuit.
Yes.
But then this just seems to fall back into this question, what can you do with a short quantum circuit? And you just land at the same old problem that you ask, building small circuits out of a few qubits, what can I do?
No, yes, okay, I agree. Okay, the thing is that in order to do a full research, you have to define what is your objective, right? So indeed, if you think of the Shor's algorithm, it's not something where you optimize on a few qubits, right? So for algorithm that, for a real quantum computer, not for a NISQ quantum computer, then you need something a bit more scalable than optimizing overall possible circuits and so on. Probably for a NISQ, you can try to do that and indeed try to see what is a set of states that one can reach with a short circuit, and these are the ones I would call useful. And you could even check whether one of those guys actually appears in, these I didn't try. I mean, what is the highest tree size of a state that you can, but since I cannot compute a tree size if you give me the state, you know, it's a little bit, I mean, if I had a MATLAB program like Nicolas Gisan likes to do, right, that you give me a state and it gives me the thing, then I would have already done it, right? You go through some circuits and you compute. But, oh, by the way, maybe I should have told, because some experimenters may be in the room, that the maximal tree size for 4 qubits has already been implemented even before we spoke about that for another reason. So someone else had found some good reason to take 4 entangled photons, do some post-selection, and compute those statistics. So it's feasible in the lab, right? It's not something you say, wow, this is 4-qubit state, is super hard. It will require, I don't know what kind of linear optics circuit or non-linear optics. No, it has been done. And by the way, without that motivation, for a completely other reason.
One question.
Yes?
Have you checked whether the number of branches can be somehow related to the CNOT complexity? Or the complexity?
Excellent question. Yes, I checked, and the answer is no. Once you put a CNOT, I did it 1 year ago in full lockdown, one of these days where I didn't know what to do. I think the CNOT removes you only one branch. And after that, because the CNOT essentially what it does, you can, yeah, you could probably transform these two into something that, but then it is not, yes, but I have done something and it doesn't help that thing. It helps only at the last step, if I remember correctly, of the decomposition. Yeah, so yeah, I tried something. Maybe I didn't try all that I could try. We can discuss later. But I tried something with a CNOT rank, and yeah, it doesn't help. Okay. Yes.
So, on the product state, which is just minimal tree.
Yes.
On the epsilon ball of this, so this cannot. So in this epsilon ball, you can't really distinguish with this product state, but.
Correct. Yeah.
But there's products. There's some free supported state, pure state,
Mm-hmm.
in terms of standard basis.
That have a lot of yeah, definitely yes.
So are you saying this? But so at least are you saying this should have large tree size or small tree size?
We studied the epsilon tree size only in these cases, and what happens is that okay, I don't know for the small tree size. What I know is that for the high tree size is completely unstable. So there is a phenomenon. By the way, the people like Stefano Mancini and all these people, they will tell you that this is there is a name for that. It's some algebra there, and then you go down for the some other. So indeed, this one is stable, but as soon as you put an epsilon there, every W state class can collapse in some direction to the G and Z class, well-known result from the early days of quantum information. So if I put the epsilon in the suitable direction, of course I could put in the wrong direction, then this collapses to 6, and it turns out that this one immediately collapses to 14. So indeed, these two are somehow accidental. Within a ball of radius epsilon, even within pure states, I immediately find something, for any epsilon, I immediately find something where the tree size collapses too low. This one is stable. So I need to put a significant epsilon before I yes, or some other, there are some names, some big names that are there, and then and we try to collaborate with them, and then again, all that came out is that definitions and definitions and definitions, but even they, the Stefano and his postdoc or PhD student, I don't remember, couldn't get any further result. We tried for 5 qubits, because in their paper they have something for about 5 qubits, and there are closures and whatever and so on. So I tried to tell them, can you write down a state in that closure? Because I conjecture that my maximum tree size is there. No, they cannot write down a state in that closure. It's the closure of the set, so whatever, right? So yeah, it's getting into mathematics that are, and honestly, I don't understand that construction. That's correctly, yes. So again, I'm not saying that this is the way to go. Maybe this is just the way to forget. But I'm just trying to, okay, the point was, can we define the complexity of a quantum state, okay?
My question was, so for a simple state with linear tree size, there's indistinguishable states that has exponential tree size?
No, I don't think so, but I haven't checked the epsilon tree size near state. And again, I have not, I mean, it's important to also define something like an epsilon tree size, right? Because indeed, if it's indistinguishable, then it's not going to be extremely useful. Right? So again, we did that operation in this case, and we found some structure and so on, but at the level of Aronson paper, for instance, no epsilon, okay? So these things are unknown virtually. Again, by me and by pretty much everyone, I think, but yes?
So just one final comment along Marco's comment, right? I mean, like, coming back to the tree size evidence that you have, because somehow a good measure for complexity for quantum computing would be one that has states should have a high complexity if they're difficult to simulate classically, and a low complexity for quantum, so that they're easy to compare, right? These are the two ingredients you look for.
Yes.
And so now you have the evidence that the short state has a high.
Yes. And a few others. There was another.
But you don't know that everything. Well, you do know that everything with. Do you know that everything with a low tree size is easy to compare?
No, that's called the Three Bpp Conjecture. And even Scott Aronson was not able to solve it. So indeed, there is no proof that the low tree size, in our paper we have a wrong claim. We thought that we could prove that high tree size is needed for measurement-based quantum computing, and it's written like that until Robin Trausedorf 1 year ago pointed out to me that what we proved is the first step, but we didn't prove that the subsequent updates, right? In measurement-based quantum computing, you need to measure something and update the state and so on. So we have no claim about the subsequent updates. So because of that, our claim is not correct. And so also for measurement-based quantum computing, until last year I would have told you to have proved it for measurement-based quantum computing. The answer is no. We still don't know if this is a necessary condition for, in some cases it's clear that you can simulate the thing classically, but no, there's no, even that is not known, and it's a complexity class, probably one of the most irrelevant ones in the whole zoo of complexity classes. Yeah, good question.
Thanks.
Yes?
But for example, these determinant states,
yes?
are they used to compare on a computer?
Good question. Okay, so that's another question we didn't explore at all after the failure of this, is whether this measure of complexity has anything to do with complexity in the lab. Of course, complexity in the lab is a bit hard to define because, what can be done, it's a little bit ill-defined, right? But yeah, we don't have an idea, so we don't know, for instance, how. Okay, we also know some states that are, what is called these? Some graph states that have high tree size complexity, and that can be, however, created. So we have as this one example of a tree size state with high tree size that can be created with a short circuit. That one we have. Not knowing if it's useful or not for any particular protocol, but at least an example is a graph state. There are some graph states that have high tree size complexity, and however, you can essentially create them by playing with the generator of the graph, with the what do you call this? The stabilizer group, and then so it can be certified in a sorry, not created. Created we don't know. Can be certified in a polynomial time. So you can certify that you have that state just by measuring the elements of the stabilizer group, and but the state itself is complex. So at least the certification would not require you a lot of time.
Just need as many gates as edges.
Yeah. Yeah, I'm not saying that anything I'm saying is not trivial, okay? I'm just saying that we're trying to put things in a different perspective. Now, since the other thing that I wanted to mention, because this is kind of related, is so let's move away from the tree size now. And the other question was, okay, there are two things that I wanted to say, but I can stop any time, so don't worry. I mean, it's just okay. One thing was about the famous topic of macroscopicity, right? That some of you are very concerned about, right? So. What about doing interferometry of large molecules, right? Does this count as complexity? Well, my statement, my understanding is the no. Okay, so doing interferometry of large molecules or of microspheres, dielectric macrospheres, is extremely important for the technological capabilities and maybe for studying things like gravity. But I wouldn't call that a complex state. And the reason is rather simple. No?
That's the reason.
No. The reason is that the state is a superposition of center of mass. But this is not a completely trivial observation, to me at least. So it's true that if you take a molecule and you delocalize between two locations, 1 and 2, so it's a matter of subsystems, right? If you take your molecule and you delocalize, you do a molecule that is just with 3 things, you delocalize between 1 and 2, well, you can say, oh, G at Z state, right? X1, X2, X3, plus X1 prime, X2 prime, X3 prime. But of course, I could also change representation and go to center of mass and relative coordinates, and this would become something like, well, center of mass in 1 plus 2, and the relative coordinates at the same distance, so I don't know how to write it, R2 minus R1, R3 minus R1. Change of reference frame, if you want, right? So this is related also to change of reference frame. And here, I mean, I have the superposition of 1 quantum degree of freedom with some product stuff. What's the big deal that this gives interference, right? If I'm a theorist, so are you going to contest these, right? Superposition of a single degree of freedom. So this, for me, begs the question of, I mean, this is a question that's been debated in the literature also by some philosophers, the question of subsystems, right? Of course, we as scientists, we go to the high school, we told them that since at least 150 years, we know that matter is made of atoms. So if matter is made, if atoms is what is real, then yes, this is just G at Z state. If center of mass is what is real, this is just now, as far at the level of the theory, at least that we have, your metaphysics is your problem, my metaphysics is my problem. At the level of the theory that we have, these two are so far perfectly valid choices of subsystems, right? But of course, this is entangled, this is not. And this is a non-local unitary transformation, right? That transforms the center of mass is not a local unitary. So this is for me another question that would matter in the case of complexity. Can I find states, and of course the answer is yes, such that a trick like that cannot be played, or at least not so obviously, right? Of course, as Czaslaw anticipated before, I can take my W state written as whatever and just call it W. This you could say, and then I could do a non-local unitary and say this is 0, 0, 0, right? And so every single state can mathematically be transformed into a product state. Right? That's a kind of triviality. But there are two things that are not so obvious. Maybe this I can inform you that this doesn't happen for optical modes, for instance. So if you have the electromagnetic field, of course it's not device independent, so you believe in electromagnetic field, you know that all the degrees of freedom of the electromagnetic field should be described as optical modes. Right? Now, so your transformation of subsystem is not in the Hilbert space of states, but in the Hilbert space of modes. If you state with that, then there are quantum states that are intrinsically multimode. I don't know how trivial it is for you, but this one, for instance, is one of them. Every single photon state is monomode, obviously. But this one, that in mode representation is something like this. I forget all the normalizations, huh? Just for. So here I have two modes. Right? There's another way to write that, is to write it as a product state. And this would look like that. Yeah. So that's also, yes, the terms cancel, right? Because the modes. So you see that I can write it as two modes, let's say entangled. So this would be, for these modes here, this would look like 1, 1. Of course, it's not the same numbers as there. Right? I've changed the definition of subsistence in between. But I cannot write this state, it's trivial to prove. You can never write that state as something like this, a single mode twice. There are two excitations, so you need to put twice, right? A single mode applied to 0. Of course, in Hilbert space, I can again declare that this is 7, 5. Because I just do a non-unitary transformation, a non-local transformation in Hilbert space, and then I can declare that to be any state. But you know, that's getting a bit cheeky, right? Then you lose all the, so in Hilbert space you can do always a transformation that brings the state to a product state, but even the Hilbert space of modes, so if you want to keep the structure of the electromagnetic field, a state like that can never become monomode. And now that you've seen it, you can generalize this to death. Unfortunately, someone else did it before me. So in fact, apart from this one, any state that is of this type in some basis of modes is always entangled. Apart from, again, either these two are equal or this one is 1. Any other, you take any coefficient, this will always look like, in any transformation of mode, you always look something like there will be some 2, 0 and some 1, 1, or some, you cannot cancel all of them, right? Again, in modes. In Hilbert space, you do whatever you want. Here there is something that hints to the possibility of creating complex states of modes, right? So something that would be intrinsically multimode. And I think it's kind of obvious that it can be done. I think examples are known. Whether any of these examples is useful in any possible sense, I have no idea. Maybe Radim has an idea. Or, of course, the guys that proved that, when I saw the paper, I said, shucks, I should have done it myself, right? I was thinking of this thing for many times. And, yeah, and it's simple to generalize. A PRA by Sperling, probably? Or, someone knows, huh? Yeah. Correct. The last year or 2 years ago, there was a... OK, so at least in modes, we have a hope. If you stay within the Hilbert space, what we did with Nicolas Bronner and some of our students is to define what we call absolutely entangled sets of states. Another kind of obvious observation, right? If you take enough many states, there may not be even a global unitary that transforms all of them into product. Right? I told you, if you take one state, of course, I can do a global unitary transform into product. If I take 2 states, you can probably guess I also can. 3, 4, 5. If you take all of them, clearly cannot, right? Because the global unitary will just, so there are some entangled states. And in fact, the minimal number is 4. But if you take sets, some suitable sets of 4 states, or 5 or 6, then it depends on the dimension and so on, you can indeed find sets of states that in whichever global, so however you change your definition of subsystems, there will always be some entanglement in the state. Now, this was published in PRA for the following reason that, and this I just tell you how I think. I did not go 1 floor down to ask Christian Kurziffer to spend 5 minutes in the lab aligning polarizers to create those 4 states and making tomography. Why? Because it's pointless. Okay? The result is in the theory. And the fact that experimenters can create 2-qubit states is known by now. Okay? So, you know, that's why, and first, if I would have been smarter, I would have put a couple of tomographic things within the experimental demonstration of a, and then we probably got in PRL, but, you know, these are games that I don't like to play. We tried PRL anyway, but we got trashed as usual. So, but anyway, so apart from these political things, this political thing was also meant to tell you something, is that I have not found a reason to ask experimentalists to implement these things. But maybe there is. So again, in particular, I have not found an operational interpretation, right? Because just, again, to create some density matrices, compare the density matrix with the theory and say, oh, yeah, it fits the theory, it's pointless. But maybe there is something useful to extract from those sets, right? From absolutely entangled sets. Again, what was the deep motivation behind? Again, complexity. Again, the idea of trying to secure some entanglement against even changes of reference frames like this one, right? Clearly, the GZ state collapses immediately because you just change into that, right? So that would be. And again, these absolutely entangled sets, but I can finish with these. I know I wanted to say something stupid before finishing, but something else stupid before finishing. We happen to invent a new field of, a new small subfield of mathematics, because only one guy, inspired also by quantum computing, by Norbert Lütgenhaus' work, had come to this same idea in 2019. So the question is, given this is for those who are really mathematically oriented, there's nothing on that. Given a gram matrix of rank dA times dB, can it be written as a Hadamard product of two gram matrices of rank dA and dB? Hadamard product is the product, not the usual matrix product, it's the product term by term. So the one that the bad students would do, all right? The A, B, C, D, E, F, G, H. The Hadamard product is really A times E, B times F, C times G, D times H. It is not invariant under any symmetry, and so it's again a mess. There are chapters in textbooks on it, there is research and so on, but this problem, whether a given gram matrix can be decomposed into this kind of decomposition, we seem to have been the first one to address it independently of the student of Norbert, both of us inspired by quantum information. So if someone is interested in pure mathematics, you can try to solve this problem. So we don't have tools for that, and of course don't ask me what happens if I go to 3, okay? So that's three-partite systems and whatever. That mathematician has some results for multi-partite systems. We have also a few, but complete mess. Okay, last point, just to finish, is this is something that apparently Marcus has ended up on the same problem for a completely different reason, is one of the things that frustrates me most is in this moment in quantum foundations is that there is no single toy model with a real Heisenberg cut. Now, you know that all of you now will tear their garments. Heisenberg cut, we all know that it doesn't exist. It's arbitrarily movable and so on. Yeah, we also know that there's no fast and light communication, but we played with it and we got a great result some years ago, right? The fact that the communication must be infinite. That's my only contribution to science that started from my brain and finished it. All the others, I just took other people's work and worked on it, right? But this one really came from me. We found a proof that if you want to simulate entanglement with communication, the speed must be infinite. So it's useful to play with toy models if you don't believe in them, right? Now, there is no toy model, no toy model at all that has a real Heisenberg cut. Something where we would say, a molecule of this size is quantum, and I am not. And in between, there is a boundary, or there is a smooth something, and so on, that makes that there is a transition from being quantum, from being non-quantum, or less quantum, whatever, right? So what I tried is this, and I will tell you why I stopped. It's the same reason why Marcus stopped 2 days ago. I tried a model, of course, super toy and completely wrong, nothing to do with reality, where 2 systems can be entangled, but not 3. That would be a kind of way of putting the Heisenberg cut. I can entangle 2 systems, but the third one that tries to come in, but there's no place, okay? What is the problem with that? Well, the space of state is kind of obvious what it is, right? There are some guys that are entangled A, B, C, some guys that are entangled A, C, B, some guys that are entangled B, C, A, and then in between, so I'll draw it like that, and in between there is a small part where they are separable. And actually this part would be, in terms of parameters, if I assume that this is just described as normal quantum things, in terms of parameters, this would be a measure 0, right? Because, well, there must be essentially product states, right?
Sorry, is this quantum mechanics, or it's...
No, so okay, my thing was, okay, here must be quantum of that type, so I must be able to describe quantum...
Convex combinations of the states that are separate.
Exactly, then you cannot do convex combinations, first of all. I mean, you can do convex combinations or in probabilistic sense, but you cannot do pure state like G and Z, for instance, right? Yes.
But it's the same state.
Well, okay, yeah, I mean, for me, the reason to abandon this thing, apart from kinematic considerations, yes, it's true that there are some that you can change the order, but for me, it was more dynamical in this case. And it was, okay, let's suppose I prepare a state in this sector. I mean, I cannot forbid anybody to create now an interaction here, right? So this state number C really wants to come in. And now what can happen? Well, either nothing, you declare that, no, once you are here, you stay there. This gives a complete trivial world, right? Then everything is stuck. Or the only possibility is that it transits, no, BC, I have to go the other side. It transits here, it breaks somehow the entanglement before going to the other sector. But this is a completely, in which basis does it break the entanglement, right? It becomes completely underdetermined or arbitrary. And I'm sure that you can think a bit and you find 7 other problems why such a model would not work, right? Marcus noticed that it's non-associative indeed, right? You start doing a gate, and at some point you add another qubit, and this qubit, there's no more place for you, right? So if you have to put the gates in the other order, then, so he was doing the GPT kind of structure for that, generalized probabilistic theory. Okay, let's not discuss on this, it's obviously nonsense, but my challenge that I want to leave you with is, can you find a toy model, whatever it is, where there is something that looks like a Heisenberg cut, not like the spontaneous collapse models, that's a different thing, right? That's more like the spontaneous decoherence, but something like a real Heisenberg cut that tells you that big objects are not quantum. And then we could play with that model and try to falsify it experimentally in a way or another, right? Yes? I wouldn't go so far because, it gives contradiction with thermodynamics as we formulated it within quantum theory. But
can you be more specific? What do you mean it's not quantum?
So, okay.
Within quantum theory is not quantum?
No, I believe in quantum theory for all the experiments that have been done. Yeah. I believe that I am not a quantum object. Never. I'm not. You should not describe me ever, or the Schrödinger cat, as a quantum object. I don't have a theory that does that. I only effective theory that says, well, yeah, don't worry. You will never do any quantum effect for every practical purpose, right?
Would that not then reduce the universality of quantum theory?
Yes, yes. I'm absolutely convinced that quantum mechanics is not universal. That's a deep conviction.
So you would like somehow to combine then quantum with some non-quantum.
Right. I would like to combine, correct, quantum with something, a smooth transition to classical, and real classical in a sense. So it's a classical that is not, again, as a theory, I don't believe neither in quantum nor in classical. I believe the world is the world. That's our theories, right? But at least as a toy model, again, something I feel very constrained. As you may know, some of you, I tried a lot of things to modify Bell theorem or whatever. Let's say, adding things, the Leggett inequalities you guys also worked on and so on. We also work on that. And we always find that whatever you try to introduce a little bit of classicality there, but immediately as an experiment that kills you, right? You can't do that. Yeah?
Can you explain better as the answer what is that you want? You don't want like irradiating mini-Weber, so objective model. What is that Maxion? Breaking the linearity, so you want to keep somehow linearity.
I think because what I would like is, okay, right? What I would like is to have at the kinematic level and not at the dynamical level. So I wouldn't like this to be something that happens. Also, it's not that I am quantum for half a microsecond and after that I am no more. I am not quantum, full stop. The grand Weber would tell you that a big object decoheres very fast, right? And I want this big object not to be quantum at all, not even at the beginning. Of course, contradicting everything and Marletto-Vedral-Bose, yeah, sure. Yeah, I don't believe in quantum theory as a universal theory of the world. I really don't.
It's the other way around, say.
General theory to replace it, but there's also no prediction within quantum theory that would even tell you that you have something like a macroscopic superposition or something, right? Or it would tell you that if you want it and want to detect it, it would be infinitely.
Yeah. You're right. Yes.
So it's not like quantum theory predicts something on the classical level that's not seen.
Well, I mean, quantum theory plus open systems predicts that indeed we don't see quantum effects at a very large scale, but it still predicts, you still start within quantum theory and you say that something happens, right? I would really like to have a toy model where something can be not. I mean, of course, there are works like Michael Hall and Reginato have tried to do mixed classical quantum dynamics, and they always honestly admit that it doesn't work. So it's perfectly possible that this plan is. My hope was to have it kinematical, so to have at the level of the states and not at the level of some effective dynamics or non-effective fundamental dynamics that maybe it's really impossible. Maybe you really don't get anything interesting if you try to play the level of the states, or maybe the whole language is messed up, right? But just
there's something which should also, I think you addressed, Marcus, is that imagine that it is correct one. However, then you say, okay, this is now a huge get, now I want to verify this. And then I realize, oh, sorry, but my interferometer has to last for longer than the age of the universe.
Yes, yes.
And now you have this
I've seen that you have also done that calculation. Okay, I did it.
Then you have this uncomfortable situation, which you can say from principal point of view, quantum theory is correct, but what does it, you expect the fundamental theory to take into account also, to be more general than quantum theory, take into account that this is not practical.
Let's put it, let's be honestly, right? If we had evidence that something we expect to be quantum because it's very isolated is not, then we would all be working on what's happening, right? So it's clear that at this moment in time, we don't have any evidence that that quantum theory does not apply, but yeah, I would like it as a toy model. That's all that I'm saying, to play with it. But I agree with you that, yeah, indeed, in this moment, this is not something that is a pressing evidence, incidentally, like quantum gravity, right? There's no pressing evidence that we have a phenomenon where there is contradiction. We are coming maybe closer to that than to this because of the, but.
This connects your work on complexity, like if they are too complex.
Yeah, that would be a possibility. So here it was just entanglement, right? But you could think of something like, this was just a toy model with entanglement and it failed miserably. You could think like if the states become too complex, somehow that they don't exist anymore. So those states are not even, you should not write them down because their nature does not follow that theory. Right? Something that would be the, but yeah, we are far from that. Yes?
Yeah, so I'm very sympathetic to both of these ideas. That you know, some states might be literally too complex to prepare with the resources available, you know, even in the universe, or even that any physical agent could have. But on a much more trivial level, when you talk about the kinematics, and probably this is what some of the people you mentioned tried and it didn't work, but I mean, you could just say, well, we have a big C-star algebra, and it's got a block structure. And, you know, it's like an abelian algebra tensored with a non-abelian algebra. The abelian algebra is classic.
Yeah, that's probably what exactly. That's exactly the Belafkin solution that essentially says, let's start by postulating that these things are like that, and then I don't like it either. Yeah.
How does it not fit your?
It might fit. Well, I mean, because I wouldn't. I mean, this gives how do you call this? Direct. Is a direct sum, no? It's not a tensor product, so it doesn't. It does tells me that there are some parts of the states that collect here, but it's not. It doesn't tell me how it. I mean, this motivation was meant more by growing the system, right? And not by. With the identity, okay. Okay. Yeah, okay. I was thinking more in terms of within the tensor product structure to try to cut some edges at some point, right? But that might that kind of formalism might give an edge in a sense, right? Now you have tensor. Okay, well, I have to think about it. Yeah, thanks. Yeah. Maybe we should finish at some point, but yeah.
How about the soft cut or forbidden quantum state that cannot be generated by a polynomial along quantum circuits?
Okay, but that's another thing that, okay, I tried also that. I tried to say, oh, the circuit must be shorter. Then I showed the draft to Berger-Englert, and he told me, when did the electromagnetic interaction between the proton and the electron stop in the hydrogen atom? We like to think in terms of gates, right? I can have these gates. I mean, our bloody hydrogen atoms have been around since the creation of the universe, right? And the electromagnetic interaction has not stopped. So, thanks Berger, as usual, you go to talk to Berger-Englert to get physical feedback, right? So an idea that at some point the interactions, in our quantum computer we will not be able to create that thing, but the universe had that quite some time, of course not exponential time, only 13 billion years, right? But at quite some time and we have no evidence that the electromagnetic interaction is decreasing, right? So yeah, I have that's in my draft that never published. That's the toy model I explored. What happens is a class of states such that I can at most allow, I divide it in qubits, and I can most allow n entangling gates before no more, right? Sure, it's just falsified by the hydrogen atom, which is kind of stupid, right?
Yeah.
I think we have to finish. There's no, maybe there's a chair person more or less, but